All right, let's continue our discussion of using truth tables to assess validity. So as you see in this example that we did in the previous tutorial, we constructed a truth table for this argument, and we discovered that there were no rows in which the outputs yielded true for the premises and false for the conclusion. That means it does not violate the definition of validity, which, as I'll just remind you one more time, is if the premises were true, the conclusion cannot be false. And because of that, we decided this argument is not invalid, or informally, we can say the argument is valid. So what I'd like to do now is show you what happens when we have an argument that does violate that definition. So let's look at this argument. P and Q imply R. P, therefore, R. All right. This argument superficially looks a whole lot like the one we just did, but let's find out how it behaves in terms of its truth table. So we will construct a truth table for the premises. The premise P, conclusion is R, and as we did before, I like to use two lines between the premises and the conclusion just to keep organized, and two lines between the premises and the input values. Once again, we have three distinct variables, P, Q, and R. That means we'll need 8 rows. So we'll do true, false, true, false, true, false, true, false. And for Q, we'll double the alternating factor, true, true, false, false, true, true, false, false. And now we'll double again, and we'll get 4 trues, true, and false, 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 false. Okay. Now let's calculate the value for this first premise. Again, it's the most complex, so we have a major operator here, the material implication. We have a minor or a level 2 operator on this side of the branch. On this side, we have no operator, so this side terminates. So we have to calculate the output of the level 2 operator first. So that's P and Q. Again, drawing the input values from the input columns, but we go one row at a time. We'll have true and true makes true, false and true is false, true and false is false, false and false is false, true and true is true, false and true is false, true and false is false, and finally false and false is false. So that takes care of our level 2 operator. Now, we'll feed the level 2 value up to level 1 and draw the value for R from the input columns, again, one row at a time. So in the first row, the input for the level 2 operator is true, and the input for R is true. So true implies true is true. False implies true is true. False implies true is true. And false implies true is true. In the fifth row, we have true implies false, which is false. False implies false is true. False implies false is true. False implies false is true. So we're finished with this column. Now notice this is our output value for the level 1 operator, so that's the value we want to look at. That's why I draw a line through the values that we no longer need to pay attention to. As before, P has no operator, the second premise P, so we just use the value of P from the input column, one row at a time, true, false, and finally we have R, again, no operator, so we're going to take the values from the inputs. All right, now, as before, what we want to do is look at the truth table in the light of the definition of validity. So again, the definition of validity says if the premises were true, the conclusion cannot be false. So to save time, let's look at the rows where the conclusion is false. So that's the last 4 rows, obviously. So now when we look at these rows, we discover, see, in the 5th row, one of the premises is false, so that's not a problem. In the sixth row, one of the premises is false. But now look at the seventh row. In the seventh row, we have both premises true, and the conclusion is false. That directly violates the definition of validity. So let me explain the theory behind this one more time. Since these input values exhaust all the possible combinations of truth values that these expressions could have as inputs for P, Q, and R, it means that there's no other situation in the world that could happen as far as these combinations of truth values. In other words, this is the whole range of possibilities. There is nothing that we haven't captured in the truth table. Because of that, the behavior of these expressions on the premises and the conclusion side are exhaustive, as we say. In other words, we can look at this table and we can tell everything that these expressions could ever possibly do because we've exhausted all the possibilities for inputs. So that means that in this truth table there is at least one possible situation, namely when P is true, Q is false, and R is false, that this yields true premises and a false conclusion. It only takes one row because the definition of validity doesn't say anything about how many times. It just says if the premises were true, the conclusion cannot ever be false when an argument is valid. So clearly, just one example like this row is enough for us to diagnose this argument as invalid. So now compare that with the previous example. In the previous example, the same reasoning applies. These are all the possible inputs. These are all, there we go. Let's get that visible. These are all the possible inputs we could have. Therefore, these are all the possible outputs we could have. And nowhere in any of these outputs do we find a situation in which the premises are true and the conclusion false. And that's what entitles us to say this argument is not invalid.